Okay, so my name is Ravindranath. I'm from STScI. I'm the lead for the JWST ETC working group. So we're going to have a lot of ETC hands-on sessions and science use cases. So what I want to do in this talk is give you an overview of how the ETC works, what are some of the key aspects of the ETC, and give you a quick tour of the key features of the ETC user interface. So to give you a little background, originally it was envisioned that the JWST ETC would be something similar to the HST ETC, but it was very soon realized that the basic design of the HST ETC is okay for the basic imaging and spectroscopy modes, but when you go to advanced observing modes of JWST, with all its instruments and complex modes like multi-object spectroscopy, IFU, chronography, aperture masking interferometry, and so on, it becomes difficult to have that kind of a simplistic approach. And also, JWST uses near-infrared and mid-infrared detectors, which have very different readout patterns. They have more complex noise properties, and all of this has to be taken into account if you want to get a very realistic signal-to-noise calculation. And also, you want to include some of the modern concepts of collaborative work and user interaction in the modern ETC. So with all of these considerations, there were some few recommendations for what is expected for the next generation JWST ETC. So one of the things was you really have to have a three-dimensional framework where you take into account the full two-dimensional spatial distribution of the flux and also consider the spectral axis. So it's like a three-dimensional ETC. And the other thing is you want to be more realistic about the way you treat the point spread function of the telescope. So you want to use more realistic PSFs that take into account all the wavefront properties. So you want something like use the PSF from something like the Web PSF tool. The other thing to be careful about is how the noise propagates, because you have all these detector properties and the noise is correlated. So you want to take that into account. And what the user is most concerned about is the signal-to-noise of the data as they use it in their observations. So you want to include some of those aspects, like how exactly do I extract the data, how do I do the background subtraction, and the different strategies that you use for aperture photometry or for spectroscopy, they're different. You want to take that into account, all into this unifying concept of what's called an observing strategy. The ETC should also be sufficiently fast, because this is a proposal planning tool, so you want to explore the parameter space, so you will be varying the parameters and doing multiple calculations, comparing the results, so it has to be efficient in that sense. And also, it should be template-based to model your instrument as well as your sources and incorporate the observing strategy the way it relates to the APT template. So it's a completely template-driven ETC. So with all of these recommendations, the prototype JWST ETC was built, which later expanded into what is called the PandExo project. It has these four basic components. The first one is the ETC engine, which is basically the Python library, the entire code, the Python codes, which which actually take the data about the telescope and about your sources and computes the signal to noise and gives you the results. Then there is the other component, which is the JWST reference database, which is all the information about your telescope, about your detector, about every optical component that goes into the system, basically the throughputs of the filters, grisms, the detector noise properties, and your input PSFs, which takes care of all the wavefront properties. The third component is the web application. This is what you are familiar with, which is what you see. So it's the user interface of the ETC, and the key aspect of that is the collaborative functionality and also the ability to organize your calculations. And the last component, which of course is very important, we kept talking yesterday about how backgrounds are very important for JWST because it's working in the near-infrared and the mid-infrared. So the observations are affected by the sky background and the thermal emission from the telescope itself. So for this, it uses a separate background model generator, and the ETC basically calls the output of the background model generator for a given sky position and date of observation. And I say that it's currently only available through the web application because if you want to run the ETC engine, you can actually download the codes and all the reference data for the telescope and the detector and so on, and still run it separately. But if you want to have the background, to input the correct background, then that is not available as a standalone tool. Instead, you have to kind of run an ETC calculation through the web interface and then download the background fits file. So to go a little bit into the detail of what the ETC actually does, so like I said, I mean, although it started off as a JWST project, now it's a much bigger project called PandExo, so it's much more general in the sense that you can run this tool for the engine can actually be run for any observatory as long as you provide the correct, appropriate configuration files and the reference data. For example, it's now also being used for WFIRST by providing the WFIRST reference data and WFIRST PSFs and so on. So basically what it does is it's a 3D sensitivity engine in the sense that it actually simulates the flux distribution in the two-dimensional spatial axis, and then it's, that spatial axis is recreated for the flux at different wavelengths. So that is the third axis. And depending on whether you're in the imaging mode or in the spectroscopy mode, you project that scene cube accordingly. For example, if it's an imaging mode, then you're collapsing it by integrating along the wavelength direction. If it's a spectroscopy mode, then essentially you're collapsing it into two dimensions, where one dimension is your spatial distribution of the flux in the cross dispersion direction, and the other axis is basically how the flux integrates as a function of wavelength. So it does include all the PSF effects. When it creates a scene, it convolves every wavelength plane with the PSF and adds the detector noise, and also takes into account the effects of background subtraction during the extraction process. Like I mentioned, the background is the sky background and the telescope background is an important component. It's both pointing dependent, where you are on the sky, and it also is time dependent. It varies over the year, so you have to specify at what time of the year you're observing. But the beauty of this is all of this is really data-driven. It's all the input that you're giving, the best estimate that you have about it, the performance of your instruments and the performance of your detector, and your best information you have about the sky. So then there is the ETC algorithm. Now, for all of this material, I would really strongly recommend you to look at this paper by Klaus Pontoppidan, which is in the SPIE proceedings. It's also available as an archive paper. So you can actually get more details of what goes into the ETC engine and the algorithm. But basically, the idea is if it's an imaging, then you essentially have the flux distribution in your two spatial axes integrated over the wavelength range of your imaging filter. If it's slit spectroscopy, then you kind of try to simplify the process by only considering part of the scene. You're creating a stamp-sized scene, which is about tens of arcseconds on the side, but then you kind of restrict the region that you're observing because you only need to consider what's getting into the slit. So that is done by using a slit mask function, which is shown here as mslit, and then you see how the light from that is dispersed using the dispersion function. For slitless spectroscopy, it's a little more complicated because the resolution of your spectra depends on the actual spatial extent of your source. So you have to take into account a little more complex slit mask, which will have the dimensions of the source. So it'll be dependent both on the wavelength as well as the X and Y extent of your object. So another thing that the ETC takes care of is the way it's defined under strategies. What you specify is how and where the signal to noise is calculated. So how the signal to noise is calculated is basically you need to know the flux per pixel, and then you sum over all the pixels that fall into an aperture that you have defined. and it's weighted by a scalar weight for each pixel because not every pixel is the same within the aperture. You also need a noise measurement related to the flux that you're measuring, but for that you have to do you have to calculate the entire covariance metrics because the off-diagonal terms basically give you the correlated noise, so that has to be taken into account. So if you just think of a simple strategy like the aperture photometry, the things that you have to define are the aperture from where you want the source flux to be considered. So you have to be very careful about where you define the aperture. And you also have to define the background region. And then the background region is basically going to be used to get the mean background that would be in that aperture. So every pixel, the flux is subtracted, the mean background is subtracted, and then the pure source flux is summed with the appropriate weights. So this is just for the simple aperture photometry, but then for the more complicated modes, you will have to, the algorithm gets more complex accordingly. So I told you that we do take into account the PSFs. The important thing to realize is that we are using the Webb PSF, which has a very realistic wavefront errors and modeling of the telescope assembly and everything. It also calculates, so the ETC calculates about 3,000 individual monochromatic PSFs because, as you remember, the third dimension of the scene cube is basically the wavelength. So you're creating the scene, the flux distribution for each wavelength, and then convolving it with the monochromatic PSF. And the PSFs are subsampled by an integer factor of the detector pixel scale, pixel size, and the final PSF actually, because you're calculating it for every plane, the final PSF actually depends on the color of the object as well. Now, for the ETC backgrounds, like I said, we do take into account the ZODI. The background model generator is what is used, and it includes the zodiacal light, it includes the galactic cirrus emission. So that's really the in-field contribution of the background. And then you have the stray light that is scattered by the telescope components into the field of view. And then there is a thermal emission from the telescope itself. And as you can see, the red line here is the thermal emission from the telescope itself, which becomes very dominant at wavelengths greater than 15 microns. And both the zodiacal light and the stray light, they're both dependent on the position in the sky and as well as the date. So there are two ways in which you can compute the background or use the background in the ETC. You either use a dated background or you can use a dateless background. But even for the dateless background, you have to specify the position on the sky because what you're doing there is you're considering either the 10% or the 50% or the 90% percentile of the background values in that particular direction over the visibility period. So even when you're using a dateless background, always make sure that you actually use the correct position. I quickly want to go through the web application. I'm just going to run through this. Yeah, you'll see more of it in the demo. So the key aspects of the ETC web application is all of your calculations are organized in what is known as the ETC workbooks. Within the workbook, you can create multiple sources, and you can have a source library, which you can then use to create multiple scenes, which means you can also have a scene library. You can use the same scenes and the sources for multiple calculations using different instruments, different modes, and you can efficiently compare the results from the different calculations. And you can also share the workbook with your collaborators, so that's an additional. And a big advantage is that all of your images and plots that you see in the ETC outputs, they can be downloaded as FITS files, and then you can analyze them using your own software. So you can do more than the things that are implemented in the ETC strategy. So quickly, the interface just looks like this, and the recommendation is to always log in by using your MyST user account, because that preserves the workbook even after you log out. And also, in case you happen to delete or lose your workbook, there is a way for us to go back and trace the workbook and get it back to you. Whereas if you're an anonymous user, then when you log out or when the session is terminated, you pretty much lose all the work that you've done. And all your available workbooks will be listed on your login page. So you can organize and save your calculations. Each of your workbooks will have multiple sources and scenes. They're all persistent in your MyST account. And we also provide sample workbooks. You can see there's a get a copy of sample workbook. So for different instruments and modes, we have examples. So you're not really starting from scratch. You have something to train yourself. Another key feature is reusable scenes and sources. So you can see in these figures I've shown they're the same sources, but then you've created two different scenes using the same sources. The other key feature is the copy and modify workflow. You don't have to start from scratch. Every workbook does have some default calculations that are provided with reasonable defaults. So you can just simply copy the calculation and modify the parameters and then explore the parameter space. You can also copy and modify scenes and sources. You can upload spectra. It's just a 2-column ASCII format or FITS file, and you have wavelength in one column and flux in the other. And here, I've given you 2 commands here. You will have the slides after the presentation. So I've put in 2 commands here, which you can use to make sure that your input spectrum is compatible with PySynfot, because then the ETC will handle it correctly. And then your uploaded spectra will appear in the Continuum tab for you to then assign it to your sources. Another key feature is the batch expansion. This is very important because it lets you explore the parameter space. So you can duplicate a calculation n number of times by changing only one parameter. For example, you can run the same calculation with the same scene and sources by simply replacing only the filter. So that helps you understand how the signal to noise varies as a function of wavelength. Or you can also vary the exposure time parameters like n groups and integrations. Now this becomes very useful because you can actually see how the SNR changes with exposure specification. So if you want to go for a given exposure time, you can think, what is the most efficient way to do it? I mean, should I increase the number of groups, or do I gain better by increasing the number of integrations? And you can compare the 2 calculations to exactly see how your signal to noise is varying. And then, like I mentioned, and it's a tool that enables collaboration with your team. We encourage teamwork, in fact. And the shared workbook, you can assign privileges to whoever you're sharing with. You can give them read access, you can give them write access, grant or revoke. And the advice is to always, tell your collaborator that you're using the workbook because you don't want accidental clobbering. Okay. I'm running out of time. So just to quickly give you an idea, the scenes and sources page, when you look at that particular tab, all of the top panels are basically where you define your scene and sources and the properties. Everything on the lower panel is a visualization of the scene that you've created. On the calculations page, your left upper corner gives you a summary of all the calculations you've done. The right-hand pane allows you to configure the calculation, your instrument setup, detector parameters, backgrounds, and so on. Everything on the lower pane is essentially the ETC output. As I mentioned, ETC outputs the 2-dimensional signal-to-noise ratio map. It outputs the detector images, which you can use later, because you can download all of that as 2-dimensional FITS files. It also gives you a map of the saturation. If there is no saturation, your saturation map will be blue. If there is whatever is in white is essentially partial saturation, which means somewhere along the ramp things got saturated, but there are partial ramps that you can still use. Red corresponds to full saturation, which means the very first group is saturated, so you cannot recover those pixels. Again, you can have 1D plots of the extracted flux, sky background, and signal to noise versus time, and signal to noise versus wavelength. All of those can again be downloaded as FITS tables, and you can just plot them using any of your favorite plotting tools. The reports pane is where you get all the calculated scalar values. It gives you warnings, which you should be aware of. Not necessarily a showstopper, but you should be aware of. Errors are things which prevented the calculation from completing, so that's a more serious thing. And downloads is the tab which allows you to download the entire tar file of all the intermediate products. And the reason why I'm stressing on the download products is because it really it's almost like a simulation of the data that you're going to get. So there is a scene that I created for slitless spectroscopy for a redshift 3 galaxy, which has a central AGN and an outflow. And you can see the ETC has essentially produced all the direct images and the GRISM images with the nearest wide field slitless mode. And the leftmost figure shows you a combination of the direct images taken in the 3 filters, and these are the GRISM combined with the 3 different filters, and you can see that there was an H-alpha emission which was redshifted to the 200W filter, and you can actually see that. So this is my last slide, where you can get help on the ETC. So we do have ETC documentation. We've provided a large number of articles there which pretty much go into the detail of each feature of the ETC and how to do calculations, how to create scenes and sources and so on. If you don't find that in the documentation, then please feel free to reach us at the JWST help desk. Thank you.